So thank you everyone for joining. I'm Nicola Asker and I'm on the Midlands Committee of the Pipeline Industry Guild for the Professional Development Network. So we try to organise a range of events to help sort of younger, early career members sort of get to learn more around the industry, outside their own business. And we've organised this talk with Robert, who's going to be talking to us all about all sorts of interesting hydrogen materials research that's been going on at National Gas. The call is being recorded, so they'll be available on YouTube in a few days, so you can share it with other people. And we'll have Q&A at the end, so you can drop things into the chat if you can see it. And if you can't, then you can always come off mute at the end and ask a question. So with that, I'll hand over to Robert.
Brilliant, thank you, Nicola. So good afternoon, everyone. Welcome to this webinar today. As Nicola said, my name is Robert Best. I work at National Gas Transmission as a hydrogen innovation engineer. Based in Warwick. I've been there for coming up to three years, well, 3 years in December. So, and all that time, my focus has been on the energy transition and focused on materials, looking at the impact of hydrogen and other gases on the materials that make up the NTS. The presentation webinar today is entitled Delivering Project Union. So I'm going to talk you through the kind of strategy that we have at National Gas for developing the safety case and all the evidence required in order to enable Project Union, and I'll describe what Project Union is as well. So this is the contents, so I've got about 20-30 minutes to talk you through this today. So I'll talk a bit about National Gas Transmission. I think probably the vast majority of people know who we are, but I'll give you a quick update on that, and then really focus on the energy transition and the work we're doing and the case we're putting together to enable that. So talk through some technical evidence and touch on a few projects that I've been running and my colleagues have been running relating to developing that technical evidence that feeds into a safety case, and then talk about the process that we're going to follow to pipeline specific assessments to enable repurposing or transition to hydrogen or any new gas, and then I'll summarise at the end. So National Gas Transmission, many of you I'm sure are aware that we're the transmission system operator, the gas transmission system operator in Great Britain. So we have over 5,000 miles of high pressure pipeline covering from north to south in Great Britain. Over 500 above ground installations, so that includes compressor sites that moves the gas around the country. We feed into a number of different direct connects, for example, power stations, industrial users of gas, storage sites as well. We have interconnectors into Europe, mainland Europe, and also into Ireland. And obviously we feed into the distribution businesses throughout the networks throughout the country, and they deliver gas to people's homes and to commercial properties. I like the stat that 3 times the energy is transported from the gas grid compared to the electricity grid. So we're really key in terms of the amount of energy that comes through our network, and as a result, the amount of carbon that we kind of that's kind of through our network. So that's a really key thing when we talk about net zero and decarbonisation. We've got a lot of energy in our network which is used at the moment and needed at the moment. So we really part of the solution to making sure that we can decarbonise the UK. And of course, from an electrical power perspective, with the new government's target for 2030 for clean power, currently 32% of the electricity is generated using gas, so that needs to be decarbonised. And I think we're pretty good value. So in terms of the transition to net zero by 2050, where do we sit in National Gas? So we have what's known as a 3-molecule approach. So those 3 molecules being methane. So we think and we know that natural gas methane has a role to play, a big role in the coming decades out to 2050 in terms of delivering power to the UK. We're looking to decarbonise the natural gas via blending of natural gas with hydrogen. So a blended network. So the intentions there is we have a network with methane, and over time we increase the blends of hydrogen in there, which can decarbonise. Alongside that, we have our 100% hydrogen backbone of pipelines, and that's known as Project Union. So this is indicatively shown by the green line on this on the diagram here, and this is really joining up users of hydrogen to industrial clusters and producers of hydrogen, so people who are able to produce hydrogen either from electrolysis using renewables or other low carbon hydrogen sources such as blue hydrogen, which is made from natural gas with carbon capture and storage. And the third molecule in this 3-molecule approach is carbon dioxide. So we see a big need alongside a hydrogen network for a carbon dioxide network. So this is something that we're really looking to roll out at the moment. The dark blue line is the project we have at the moment in Scotland, but the intention is to build a similar type network across the UK. Again, this is really focused on decarbonising industry and the power sector, the electrical power sector. This is a nice graphic that I wanted to put in that kind of shows again where we sit within national gas and when it comes to the energy transition. So if I just start with the blue circle at the top here with the hydrogen, so hydrogen production requires some feedstocks. So for electrolysis of green hydrogen, we need a renewable electricity supply. So there's a number of different ways we could get that renewable or low carbon electricity supply. We also need water. This is splitting of water into hydrogen and oxygen. So we need to make sure we understand the feedstock of water to enable that energy carrier hydrogen to be produced. The other way of producing hydrogen, so the conventional way is via fossil fuels, reformation of those. Currently, the CO2 tends to be is emitted, and that's grey hydrogen. But obviously, from a decarbonisation perspective, we need to capture that. So again, national gas, we feel that we fit in terms of the capture of that carbon dioxide, either into storage or the utilisation of that carbon dioxide for various purposes. That methane or those fossil fuels can also go directly into power generation, and again, we can capture the carbon dioxide from that within our pipelines from a carbon perspective. From a hydrogen side, so obviously in national gas, we're the transmission network. We transport the hydrogen from where it's produced to where it's needed. Being a pipeline network, we also have storage because within our pipes. So that hydrogen can go again into power generation, and also could feed into the distribution networks for domestic and commercial uses. And this is our Clean Power project. And within Project Union, this is, as I mentioned before, it's joining up industrial clusters. So this is a really key thing that we see hydrogen being a key player for industries that will find it difficult to decarbonise without a molecule, without a high temperature gas, for example, or even the chemical H that's required in some industries. So Project Union is really key to decarbonising some critical industries here. And then one sort of market that hasn't really been seen by national gas in the past is the transport market. And again, we see hydrogen playing a role. We know that batteries are really key in these areas, but there may be certain applications in which hydrogen is a good option. And the hydrogen can also be combined with the carbon dioxide to make synthetic fuels in some really difficult to decarbonise areas such as aviation. Will almost certainly need some sort of synthetic fuels to be created in order to become a net zero industry. So quite like that graphic kind of shows that national gas, we kind of fit in a number of these different ways. So how are we going to deliver this? So this slide here shows a kind of a pyramid, which is building evidence building up from the bottom all the way to delivering Project Union or blending, or we could also be the same evidence for carbon dioxide. So we start at the bottom with technical evidence and then move up through the various layers. So let's start with development of technical evidence. This is the kind of the baseline here. We need to understand how the new fuel, how hydrogen impacts all of these areas, and then we can feed that into standards, into the safety case, and then eventually via pipeline specific assessments into deliver the hydrogen network. So let's start talking about technical evidence. Loads of detail on this slide, but I really wanted to kind of highlight the work that my colleagues do within the innovation team and the energy transition team in national gas. So we have projects listed here, kind of, and others that aren't on here, related to all of these areas that I think are really key for for that energy transition. So the safety case obviously is paramount in our industry. We need to make sure that we have a very good safety record in National Gas, and we need to make sure that is maintained with these new gases going forward. So that's a really key thing. So a lot of evidence at the moment is feeding into that safety case, making sure we understand how these gases operate and making sure we can do that safely. Measurement is a key theme as well. Different gases behave differently, so things like gas analyzers, meters, they all need to be upgraded and changed potentially for different blends of gases and different gases going through that. Compression, all our network is designed to compress natural gas. Hydrogen has a different gas properties, so the compression side needs to be considered as well. If we're having a backbone, we need to be able to move gas around the country, so compression is a really important theme as well. Operational themes, so we've started some projects in the operational area. That's making sure that our people on the ground know how to operate these networks. We potentially have 3 parallel networks with different gases in. We need to make sure everyone has the right skills and competencies and training to enable to operate and maintain those 3 networks. Next one, energy system operations. In the graphic previously, we showed all the feedstocks. So there's interactions between our friends over in National Grid and the electricity side, but also from the water industries as well. There's a number of different things that need to all work together in order to enable this net zero. And there'll be other industries such as the transport and aviation, for example, that we need to get involved in. So there's projects to make sure that we're all kind of going along the same path and all aligned with the technologies and needs of the different industries. My area down here is pipeline and materials. So I mentioned lots of projects related to the impact of hydrogen on the materials that make up the NTS, and I'll talk a little bit about one project in a second. Data and systems, so having 3 parallel networks is going to make the kind of operation and the system, the data side, very important. With all the advances in the last few years, AI and other technologies, important theme to make sure that we stay up to date and leverage these new technologies to enable a really efficient and of course safe network to be developed. Blending and deblending. Blending is one of our key molecule approaches, so that's going to be something that we're really interested in. We've got some projects that I'll talk about, a project we'll talk about on that in a second. And then the transitional strategy. So it's all very well saying we're going to build up these 3 networks, but how are we going to do that, given the fact there's a lot of people on our island, we've got a lot of pipelines, and everyone needs the gas currently that goes through those pipelines. So developing that transitional strategy is really tricky and involves a lot of kind of stakeholder engagement, a lot of work with our internal teams to make sure that we can, if we want to repurpose a pipeline, we're able to decommission that, but also make sure that we meet our current requirements and demands. Okay, so I'll talk a little bit about the materials projects. So just got a slide on this really. So this is actually a stacked bar chart here of the materials we have on our network from a mainline pipe perspective. So these are all carbon steels of varying different grades, and you can see we have a lot of X60, quite a bit of X52, and also quite a lot of X80. And the number means the higher the number, the higher the strength, really. They're all kind of variations on a theme in terms of carbon steels, but we've got a variation of grades across our network. And this chart here shows you the build-up of our network, the National Transmission System. So the NTS was first started in 1964, and with heavy kind of growth through the late 60s and through the 70s. So by the end of the 70s, over half of our current network had been built, with kind of steady growth through the 80s, 90s and noughties, and not really much since 2010 in terms of new pipeline builds. Obviously, we've been maintaining this network over this time. So we've got a network that's relatively old. It's not the oldest. There are many in the United States and in Europe that are older, but it's it's getting on a little bit, but a very well maintained and constructed network. So in terms of understanding the impact of hydrogen on these metals, what have we done? So I initiated a project in which we got hold of pipes out of the ground that covered as many of these different grades we had and different ages that we had across our network. So I kind of split them into kind of vintage, semi-modern and modern, kind of arbitrary distinctions there. But we basically got hold of 11 pipes covering these grades and ages, and then they took them out of the ground. So a lot of these were coming from decommissioning works or diversions or things that HS2, for example, or if there's any need to move the pipe for whatever reason, then I got access to those pipes. So that's quite helpful. We took it out of the ground. We then manufactured them into specimens. Here's a couple of or 3 fracture toughness type specimens. We then put it in a chamber, fill that full of hydrogen, in this case 70 bar, 100% pure hydrogen, and then we do a number of tests, including fracture toughness and fatigue crack growth. And these are 2 properties that we know hydrogen can impact the performance of metals in those 2 areas. So we took the intention was taking 11 different pipes, testing the base metal. The welds are really important, so testing the seam welds and the girth welds, so the seam welds that join the pipe together, and then in the pipe mill, and then the girth welds that join the individual pipe spools together that are done in the field. So we tested all these 3 locations with these type specimens to get this data. And this fracture toughness data and fatigue crack growth rate data we can use in assessments of our pipelines to understand the capability of that pipeline to transmit hydrogen. Another key bit of evidence that I wanted to talk about, and I'm sure, hopefully, most of you have seen this before, FutureGrid. They've been some really good comms over the last few months on this. We've just recently finished this phase 1. I've only got a couple of slides on it, so if you're interested in this, reach out, look on the website. There's loads of really good information on this particular project. So as I said, this phase 1 is just completed, and the intention of phase 1 was to basically demonstrate the capability of our current assets in hydrogen and hydrogen blends. So this is a flow loop that was constructed of assets that have been decommissioned, again taken out of the ground. The vast majority of what we see there has previously seen some service within the national transmission system, and the idea was to kind of bolt on and weld together as many different types of assets as we could. So we've got filters, we've got valves, we've got pressure reduction skids, we've got meters, everything that we could kind of get hold of and we thought we could put into a loop was done. This was done up in Spade Adam with our colleagues at the DNV, and with support from a number of different other organisations as well. And in this flow loop, we flowed with methane, and then with increasing blends of hydrogen to 520 and then up to 100% hydrogen. And the intention of the phase 1 FutureGrid was to demonstrate that we can put hydrogen into our network and all these assets operate as expected. So lots of work to understand things like vibration and noise, and whether there's any changes and whether they match the models that we've currently got for hydrogen. So a successful project on FutureGrid, but loads of data and information. Check out the website. That was phase 1. It was completed earlier this year. We're well into phase 2. So there's 2 sections to phase 2, which is FutureGrid compression and FutureGrid deblending. So you can see this is the phase 1 loop, and you can see the compression. We're looking to go all the way down the side of this same site in Cumbria, in northwest England, and the deblending facility is going to be a bolt onto the phase 1 loop. So what is the FutureGrid compression project looking to do? So this is quite an ambitious project, really. We're going to be building a kilometre-long loop of above ground and below ground pipe work. Again, decommissioned as much as possible pipe work that's come from our network. Previously seen natural gas service, and we're going to take a decommissioned compressor and bring it up to the to Spade Adam, and then incorporate this into the loop. And the key thing about this project is we're looking to operate that compressor with blends of hydrogen and understand what modifications, if any, we need to make, and up to what level of blend these current compressor systems can operate, and then understand what modifications will be required to enable 100% hydrogen to be compressed within these current facilities. So this is all about making sure we get the kind of best value for money for the consumer here. we're using assets that currently exist rather than having to replace them with completely new pieces of kit. What does that involve in terms of refurbishment upgrades to these current pieces of equipment? The other project is future good deblending. So as I said, this is tag on to the future good phase 1 loop, and this is really looking at the future, a potential future market focused on transport, and looking at how we can deliver hydrogen at the required purity levels for different customers. So if you think about hydrogen going into fuel cells, then the purity and grade needs to be very high. For other sort of internal combustion engines or other industrial users, maybe a less pure blend is required. So this project's really about understanding the technical side, so what technologies are available, and demonstrating that they're capable of deblending hydrogen from a natural gas blend. But also there's a lot of work with the stakeholders and the market side, understanding the requirements of these different industries. We have a network that covers, along with the distribution companies, that covers the whole of the UK, and people need transport the whole of the UK as well. So we think it's quite a good match. But obviously this project's looking at the economics, but also the technical feasibility of this as a technology. Okay, so that's been talking about the technical evidence, that blue box in the middle. So all of these projects, and obviously I mentioned loads of others as well, they then feed into creation and update of engineering and operational standards and policies. So that's really key to making sure that we have everything in place to operate our network, and these then feed into the safety case. So we're developing 2 safety cases, or a number of safety cases related to 100% hydrogen and also blends. So this is the timeline for the safety case. So we're currently in 2023, 24. And this is all about generating the evidence, developing that technical evidence. By the end of this year, we will be submitting safety cases relating to low percentage blends in the NTS. And next year, we'll have a higher percentage blend evidence case created. And the year after that, we're looking at 100% hydrogen. So there are a number of regulations, gas safety management and pressure safety regulations that need to be updated to enable this within our network. Currently, we're licensed to transmit natural gas, so to do anything different, we need updates to these, and this is what all this work is kind of helping support those updates. So these updates to these regulations that will then enable blending to occur sometime this decade, and then by the end of the decade, we're looking to start the construction of Project Union, which is 100% hydrogen backbone, as I said. So we need to make sure we have all the evidence case developed to be in the right place to be able to do that. Project Union, the construction will go through into the 2030s. So there's the first section will be the plan by the end of the decade. So that's development of the safety case. So once we've done that, this has kind of all been relatively generic and general at to this point. This is more typical materials we have, typical assets we have. Also looking at specific types of assets, but not necessarily saying this pipeline is capable. So the next section is, once we've understood how we do this, we then do our pipeline specific assessments and risk assessments of those ones. So we're now at a stage where we'll select a pipeline. We want to repurpose this for hydrogen, and again, the same thing would happen for CO2. So from a pipeline perspective, how would we do this? Well, we'd look at the hydrogen design codes that currently exist. So many of you, anyone who's been working in hydrogen, will have heard of ASME B3112. This is probably the most extensive, or definitely the most extensive and well-known hydrogen code, obviously with a North American bias, but it's kind of an international standard really. And from that, pretty much all the standards around the world have kind of have been based really. So that includes our IGEM TD1 standard. So TD1 covers natural gas, but there's a supplement that covers hydrogen, and it's TD13 for pressure regulating installations, again, which has a supplement 1 for hydrogen. And these two supplements basically have copied very heavily from ASB 3112 with a few tweaks that are kind of more representative of the way we do things in the UK. So when it comes to repurposing, both these codes have sections, give some high-level guidance on how we do that. And you can see here sort of viability design assessments, then into the detailed technical assessments. It doesn't really give you much specifics on how to do that. So we've been developing our own process within National Gas so that we have a more clarity and detail in terms of how we do that, and obviously making sure that it's tailored for our network, which as I said previously, is maybe more modern than some networks around the world. So how are we going to do that? There's four kind of main stages. First one is a viability assessment. So looking at the capacity of a pipeline. So as I said, we're at a stage where we've chosen a pipeline, or we want to get hydrogen from A to B, and we've got a number of options there. So we can do a capacity assessment, making sure that the pipeline's big enough to transmit the amount of energy we need. A simple kind of hydraulic assessment on that. Material assessment as well. We know that hydrogen has an impact on materials, especially metallic materials. So we can do a quick high-level assessment to make sure there's nothing on there that we would need to, that would cause us to not want to repurpose that line. Currently within our network, that there isn't any particularly high-risk materials that we've identified at present, but there are maybe materials that we need to understand the performance in hydrogen and design appropriately. The next stage is conceptual design and operability studies. So this is more detailed sort of design review, more detailed capacity analysis, making sure that the pipeline is capable. So this is where we'd look at possibly doing things like material grouping. So we're doing some assessments. We do assessments on the pipeline from a materials perspective. And maybe we can kind of use data we've generated in other projects, the one I mentioned, in order to get an indication of the performance of the pipeline in question. After that, we then into detailed repurposing studies. So this is compliance with the codes, making sure that we do everything the codes require us to do. A fitness for service assessment. So it's really digging into the detail. So on this pipeline, what's been the impact of prior service? What are the grades? What are the materials we have? Is there any corrosion? Has there been any damage to that? Have there been repairs over time? What kind of pressure cycles has this pipeline seen in the past? All of these things kind of feed into to the assessment we'll do on the capability of that pipeline. We'll also look at not just the pipeline, but all the assets associated with that. So I mentioned compressors earlier, but the valves, the filters, identifying what meters and gas analyzers and other metrology kind of equipment we have on the network, making sure that they're capable, or we know what upgrades and replacements we need to do. And again, on a site-by-site basis, making sure that we assess all the pipework and fittings, check the pressure vessels, the control instrumentation, all those kind of all the detail, all these things that are important to operating these above ground installations. They all need to be checked and upgraded and plans made on those. So finally, once we've done that, we can then do that change of service. And so there'll be some level of venting and purging to obviously remove the natural gas and replace with the hydrogen. And then we'll be able to gas it up and pressurize it up, and then move into the operational side, operating those networks. And so and so then to kind of summarize at the end there, half an hour in, it's not bad. So National Gas Transmission, we're the high pressure system operator, gas operator, transmission system operator. We can get that out for Great Britain. Within the context of the net zero transition, we have a 3-molecule approach, our 100% hydrogen backbone, which is Project Union, our blended hydrogen natural gas network, and our carbon dioxide network, which is known as Connect. We've done an extensive test program with partners from all around the world to generate evidence. So we've led a number of projects ourselves, but we've also been partners on numerous other projects around the world. Lots of people are doing the same thing in the United States and Europe. And so we've been working very closely with those colleagues to make sure that we share evidence, share learnings, and yeah, come to the right and the best conclusions. And then finally, on a project union, so our intention is to start construction of that hydrogen backbone by the end of the decade. And that concludes my talk. So thanks everyone for your attention. Hope that was interesting. Not quite sure how we're going to do questions. We can't see the chat, but I think Nicola and Kate will be able to organise that together.
Yeah, thank you, Robert. That was really interesting. So yeah, if anyone wants to dive in with any questions. Oh, cool. Straight in there.
Yeah, hi. I have a question. Great presentation, first of all, from the both of you. And yeah, Rob, we have been both on an event where we have been learning and sharing information about the embrittlement caused by hydrogen. And one of the key observations was that there is a tendency for blending even lower percentages of hydrogen having to be considered similar to fully 100% hydrogen. I think that recently I picked up on some messaging that is potentially going to be now embedded in IGEM standards. Am I right there? Are we on that page that even low, below 5% hydrogen is a similar consideration as 100%?
Yeah, so hi, cool. Yeah, the current IGEM supplement for hydrogen is a little bit confusing when it comes to blends, although it does say that low percentages you would have to do an assessment and maybe assume the properties are similar to a high percentage. So 5% you may need to assume the properties are the same as if it would be 100%. There's some work going on within the ASME code. The B3112 code is being retired and replaced with the content of that was going to be moved into B318, which is the general gas code. And there's going to be an annex H for hydrogen that will kind of cover the content, this hydrogen specific content there was in 3112. Within that annex, there is the wording is that any intentional addition of hydrogen, you need to follow the annex. So that would include intentional blends, even at low percentage, and then you would need to do an assessment of the impact of that. So we're currently looking at ways to understand low percentage blends, what the impact of hydrogen would be. In the distribution networks, the partial pressure of hydrogen at low percentage becomes quite low, but in the transmission networks, the pressure is obviously higher in general, so the partial pressure of hydrogen is a little bit higher. So a long-winded answer, but effectively, yes, the codes say that we have to look at hydrogen, the data at low percentage blends. The data kind of backs that up as well. So I think that's something that we
and the IGEM standards make reference of a 10% boundary, and that is likely to disappear. That is still the case, Rob.
I think so. If they follow what the ASME update is going to say, then I imagine that would be removed as well. Yeah. I mean, the IGEM's a bit confusing. It does say 10%. There's low risk, but it doesn't say no risk, and it doesn't say exactly what you need to do on that. So I think the ASME code, which has been sort of a consensus engineering approach, so people from all around the world are fed into that update to the ASME code. I think that is the best, the industry's best knowledge at the present.
Thank you, Rob.
Cheers.
We've also got a question from Harry Venn.
Hiya, thank you for that. It's a great presentation. I was just wondering, when you were talking about the viability assessments, with respect to transporting the same amount of energy using hydrogen, say at 100%, what's the current thinking on how this can be achieved, given the fact that you need sort of 3 times the volume of hydrogen compared to natural gas? Are you looking at in terms of higher velocity, higher pressures, or larger diameters?
Yeah, so I think if you're designing a pipeline, a new pipeline, then you obviously take that into account. You know what the energy requirements are, and you'll size your pipeline appropriately. If you're repurposing a pipeline, then you can't change the diameter. and you can't change the wall thickness. So you're kind of limited with the pressure capabilities of that pipeline. The pressure capabilities need to be also considered in terms of the impacts of hydrogen on the metal as well, which then leaves you with velocity really as the thing that's left to enable that. So I think, yeah, it's about making sure that you understand that and you do your assessment correctly. And when you're linking up those customers and producers, you understand the energy requirements as well as the volume and what that means in terms of volume and flow rates and throughput.
Okay. So there are scenarios where likely it might go above the velocities we've seen for natural gas pipelines.
Yeah, I mean, we're doing some projects looking into the impact of that. Higher velocities could have implications in terms of noise, vibrations, potentially erosion as well. So we've got projects that are looking at those impacts and seeing what kind of velocities can be achievable and yeah, obviously safe as well. So yeah, we're looking into that.
Okay, great. I've got another question, but I think somebody else raised their hand.
Yeah, Zoe had a hand up for a second.
Hi there. Yes, I did. So I just wondered, in terms of joining the pipeline, how are you managing the residual stress that can be caused by this?
Yeah, residual stress is an interesting one and a key one. So when you're doing the fracture assessments, residual stress is something that needs to be included within that. There's guidance within the code within the BS 7910, which would be the code that we follow for fracture assessments. There's guidance in terms of how you do that. We're also looking at ways of there's some previous work being done by Rosen, a review of residual stresses in pipeline materials, pipeline welds. That kind of gives you an indication, depending on the pipe making process and the welding process and the if there's any post treatment of those, and any hydro tests as well can relax residual stresses in wells. So there's some work that's done previously on that. I know there's also work with NIST in the United States looking to do some measurements, some neutron measurements of residual stress in wells. So it is something that needs to be incorporated and included. There are guidance in some of the codes, but it's certainly something that we're following up with people like NIST, and the industry is very interested in getting some representative data. We've also got there's a project with University of Oxford and EPRI are leading supporting that project, and they're modelling the deposition of different wells and the residual stress profiles that arise from different well procedures, and then they can put they can overlay that the expected hydrogen concentrations under different hydrogen pressures. So a number of different work streams we're keeping an eye on when it comes to residual stresses.
Thanks for that. Harry.
Thank you.
Sorry, only go with the second question, Harry.
Hi, sorry. I was just wondering, with the materials testing and the facility that you're saying, will the dynamic behaviour of hydrogen be tested? So, for instance, stuff like surges in the pipelines.
So in Future Grid, there was no deliberate kind of changing in pressure spikes or velocities. I mean, they did operate at different flow conditions, a high flow and a low flow condition, to kind of represent our network, different offtakes on our network. But within that facility, there wasn't any particular pressure surge. The testing that we've done to date generates fracture toughness data and fatigue crack growth rate data, which you can then put into models to understand the impact of any kind of pressure excursions within that. But I guess at present we haven't really looked too much in that area, but we have got data that we can feed into assessment models that currently exist.
Okay, thank you.
Any last questions for anyone else? Oh, Phil.
Hi there, Phil Gaskell from Cadent. Just curious about the blending scenarios, because obviously, if we want to blend, and the best option for decarbonising is to blend at the highest point, but that be the NTS. But of course, as soon as you start to blend in the NTS, I guess you have to assume that blend will go into everything that comes off the NTS, i.e. every distribution network. And if we've got lots of projects in distribution level. There's 4 of us and you guys all working on blending projects. If you blend in the network, to some extent, it sterilizes our capability to blend further down the network, and vice versa. If we suddenly come up with a project and we move ahead at 100 miles an hour and we're a bit quicker than you guys to instigate it, then whatever we do at a lower tier may well sterilize your capability upstream to blend. So my question is more about collaboration. How are we making sure that we're not racing each other and the first person wins and therefore nobody else can do it? Because from an industry perspective and from a decarbonisation perspective, we need to make sure that we're all working together and we're delivering the most possible blends at the best possible places. So I'm just interested in what sort of collaboration, what forums are ongoing at the moment, looking at making sure that we're all talking together and we're all following the same path.
Yeah, it's good. It's a really good point, and very, very well put. I think so. We have regular meetings within with the, I can't remember what the governance. We've got the gig governance groups, and there are other NSIB, NSI groups that exist. So we do talk with each other a lot, and obviously the funding arrangement means that the data that we generate and the data that Cadent generates and SGN and everyone else is available for everyone else to discuss. On the materials level, we have a monthly meeting that discusses the projects that we're doing. It's a really good point about blending and the positions and locations of blending sites and the agreements that we can have in terms of enabling that. So it kind of it's all linked back to the GSMR requirements as well, and the limits that we can put on that. So I think you're right. The key thing is that collaboration. We do have groups that are already working. We've got dedicated blending team within National Gas now. So one role of theirs will be to make sure we understand how that works, so how that links in with all our end users, whether it's the distribution side or any of our current existing customers, direct connect. So yeah, it's a really good point, and it's something that we're aware of. And yeah, we just need to work together, and obviously we're all kind of driving towards the same goal, but we are separate companies, so it's a tricky one at times.
And therein lies the conundrum, doesn't it? We're all sort of in competition with each other, but we're all trying to get to the same end goal. So I'd be interested to be involved in any forums that do spring up around those, sort of making sure those people are in the same room talking about it, more from an operational perspective rather than a strategic perspective.
Yeah, okay. So yeah, certainly if you just I guess we can share emails, and we can
of course
we can then I'll put you in contact with the blending team. They'll be the best people to go forward from that.
Fantastic, thank you.
Thanks, Phil.
Okay, if there isn't any other questions, then I think that's a good time to wrap up. Thank you again, Robert, for that. It was really interesting. And the recording will be available probably in the next few days on YouTube, so feel free to pass it along to anyone who missed out, and check out the website for other upcoming events. But thank you all for joining. We'll see you again at another event.
Thank you.
Thank you.